在哪？
进来，我看一下，这马上。
Share. Enable this. Enable sharing.
How about now?
Do you need to enable slide sharing or?
Sorry. How to enable? Okay, now. Still cannot share.
Sorry, I'm not able to share.
Don't know why.
He cannot share.
Yes.
So you have to give him the permission as a host. But
attenders.
yeah, right. So you have to promote him as a host. So now he can share.
How about now?
Yes.
Okay, you should turn on the video.
Okay, like this. Organize. Engineers, researcher from Faculty of Information Technology at Bond University. Today, I'm related to some book as well. Books with training on a mobile machine for unsupervised implementation. This is on work with Tuấn Nguyễn Văn Nguyễn, Quang Trân and Đinh Phúc. Okay, so it is what we propose approach to deal with the problem of documentation or DAs. So let me introduce you the setting of DAs. For DAs, we have short domain with labels. Short domain consists of many pairs of data labels X, I, and Y side. On the other side, we also present a target domain with down label. For target
Can
domain,
you
we
turn
only
down the
have
volume because I think
label
it's too big?
DI. We need to
Sometimes change the voice.
The voice is too big, I think. Yeah, I think it's I think
Okay, so push slow. How about that? How about this?
it's too small. So increase. Yeah, I think it's better.
Bio PS vision distribution of class in the domain. Thank you before. Now we see correlation between short and target domain. And for the case, we need to diminish the gap between short and target domain in a latent space. Basically, we need to learn a feature factor that possess a short and target domain to the common feature space or latent space. And in this space, we will close the gap between short and target domain. For this purpose, we define P here as empirical vector distribution of a short and target example. Basically, the particle from P consists of short example and target example. In the meanwhile, we define PS here as a distribution over the class condition distribution. So particles of PS here consist of the class condition distribution. And we examine the quantum distance or optimal transport distance between the mixture distribution P and PS. Therefore, we learn ability transportation Mach A, and also need to define distance between an example here and a distribution here. Basically, we utilize feature factors here to map both P and PS to a latent space. Here, transport P to Q, and also transport PS to QS, and we examine the auto transport between Q and QS in the latent space. Basically, we learn feature factors and the mixing proportion height to minimize water state distance between Q and QS. By doing this, we want to match the short sample to their corresponding short graph distribution. In the meanwhile, we want to align target sample with appropriate short graph distribution, hence promoting structural adaptation. Now let us talk about the solution. Particularly, we utilize a deep transportation network T with M output to approximate the transportation matrix A. More specifically, given example Xi, we apply T to GXI to predict AI, which is a role in the transportation matrix A. And water distance of interest can be turned to minimizing this total cost that's relevant to the transportation network team. Basically, to train the transportation network team here, we minimize the total cost, and we also minimize the probability. The team here must XI is open to this level. Over for we
大嫂是基于广大，
to eat
不是我，正常人，而且太丑了。首先
and after start training, given the inside
自主身体有力的这个都可以这些可以看这些
nine books
感觉很奇怪。
we involve
我也没人。好像
so he has everyone outputs
你要把膝盖做成膝盖，成这些啊。
DM denotes the property in the crowd, the first one denote the property xi belongs to target domain. We train the equator to distinguish a short and target domain similar to GAN. And also interest equator to predict correct label for short example. Finally, we come up with this training objective function to train classifier, the feature factors, and the transportation network. Here, this is the sum of phi losses, the classification loss, the loss to move a short and target domain to correct and corresponding present. The entropy based loss to encourage the confidence prediction and the optimal time based loss to minimize the total loss. To further mix up the short and target domain in the later space, we also propose a high order moment matching term. So let me walk you through that term. Given latent representation z equals x here, we define a Q order moment at the cubic tensor. Basically, an element corresponding to indication I1 to IQ in the tensor defined as a product of element in the latent representation here. More specifically, given two distribution U and V, you can think about the U here and distribution of a short example in latent space, and V here and distribution of a target example in latent space. We define their high orders moment matching distance as f norm of the mean of AQZ, Z follow distribution U, and the mean of AQZ values Z following. So this is similar to MND. As you can see, direct computation of this high order moment matching distance because it costs P power cube. That's why we need to come up with the efficient way to handle this high order moment matching term. We pattern the Q lim tensor to the vector here, and we can reach this formula for the Hessian distance that's similar to polynomial kernel, and this can be built efficiently now. And finally, we plug this into our framework to train the transportation network lead. Finally, here the last to update the classifier C, the feature factor C, and the transportation network that is summarized in this algorithm. We also conduct experiment on all mathematics in DA, and you can see that our approach, our form, the SOTA baseline by large margin. We also visualize the we use the SD to visualize the latent repetition of the short and target domain in latent space to explain why algorithm work. And you can see that the algorithm can sort out the problem of coercive in the latent space. And the target example and the short example really mix up accurately in the latent space. That's why the approach work well. That's all for my presentation. Thank you for your attention.
I don't think we have time for any question. I think the coffee break now begins. One rather tea is whatever.
Okay.
Which is actually ready to do so.
Wait.
I think given that we already have suggesting that we let the online
这个
speakers
paper 是60多页，我觉得我们昨天还是
是
later
就能刷，所以就那个可以做的。
可以
So maybe let me see whether we have
可以。你最近要投新收入到人家
就来现在听。
对对
if help
对。UPD 是怎么办？
啊，真的没有，那是真的。
看那个，确实收了，就是真的。
你说主题的时
excuse me. Alright. How do we confirm that
is here? Seriously? Let me check. Yeah.
There is only one online attenders. There is only one online attender.
Yeah.
Oh,
That's true. Yeah,
that's
yeah.
true.
Just change the
just are they present?
I can.
Okay. So yeah. Okay. Good.
Okay.
Fine.
Yes.
Am I
done.
clear? Do you hear me?
Yeah, I think
Hello, can you see my screen?
What's wrong? Because it should be.
The voicing
You should connect this with so the audio should be
Hello, am I clear?
I think there's one more part
Sorry, I think we
here.
some problem.
Yeah. Yeah. But
Oh, am I clear?
다세요.
yeah, I can hear you. But there's a bit of
should be speaker.
应该是
Can you see my screen? Hello? Sorry, I think you are muted. I can hear you, Dr. He.
Okay. So, can you hear me?
Yes, that's clear.
Yeah, so I think you can start it, but I don't think we can hear you. So I can hear you from a laptop, but I don't think the audience here can hear you. Let me. Hello? Are you?
Yeah, I can hear you.
Hello, the presenter? Can you hear me?
Yes, yes, I'm here. I'm here.
You want me mute or mute? Yeah, it's mute. It's muted. Yeah, we got an online presenter here.
Your mum says you should be playing back if you got. But if you're playing for floors, yeah.
Yeah. I think I can hear them clearly, but
Yep, that's fine. Let me just.
okay.
So the volunteers are supposed to do this, and none of them have done it so far.
Okay. Hello, can you hear me?
Yes,
Hello.
yes, I'm here. I'm here.
Hello? The online presenter, can you hear me?
Yes, yes, I can hear you, but I'm not sure whether you can hear me.
It's very.
Hello, hello, hello.
Hi, can you say something about test?
I'm on mute, so
On
I'm
mute,
not sure.
yeah,
I'm
yeah.
not sure.
Okay, sorry. Okay, so 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 sorry. Okay, so. Yeah, it's mute. Yeah.
Hello, hello. Can you hear me? Hello, can you hear me? Hello.
Hello, can you hear me now?
Yes, yes.
Hello?
I can hear you. I can hear you.
Oh, okay. Um, keep talking. Can you just talking for our test? Can you talk some words?
Good
wait.
afternoon, everyone. Can you hear me?
Yes, we can hear clearly. Thank you so much.
Okay. So Sorry about the delay again. We are solving some technical issues. Probably you can start right now.
Okay, thank you, Dr. Zhao. Good afternoon, everyone. I'm Li Zhuo from Shenzhen Research Institute of Big Data and Chinese University of Hong Kong, Shenzhen. It's my great honor to share our work synthesizing minority samples for long-tailed classification with distribution matching with you. This research comes from CUHK Shenzhen and Jilin University. As a beginning, let's have a brief review to the long-tailed problem. Just like shown in the left figure, a few majority classes dominate while more minority classes have very few samples. That's so-called long-tailed distribution. As a result, we can imagine that models trained on such a long-tailed dataset tend to be biased towards the majority classes. They often fail to recognize minority classes correctly. Intuitively, we can rebalance the long-tailed distribution by data augmentation, as shown in the right figure. As a result, the training of the classifier may alleviate overfitting toward the majority classes, which in turn contributes to the development of being more robust. However, undersampling may discard some useful information, and the traditional oversampling methods like SMOS may generate synthetic samples that do not accurately represent the minority classes distribution. Okay, our motivation stems from the idea that creating more synthetic samples for minority classes can help balance the dataset. However, it's not just about creating any synthetic sample. A good synthetic sample should meet specific classification constraints. Essentially, we want to cook with more raw materials, but ensure they are the right ingredients. As previous work has shown, a synthetic sample from a majority class can be considered a minority class sample if a pre-trained classifier identifies it as such with confidence, where a target classifier is uncertain about its origin. Okay, building upon that, we argue that satisfying classification constraints isn't enough. The generated synthetic samples should also closely resemble the real samples within the target minority classes. To achieve this, we focus on aligning the representation distribution of synthetic samples to that of real samples. So we formulated the distribution of real samples and synthetic samples of class K as two discrete probability distribution Pk and Qk. By minimizing their distance, we can effectively align the synthetics in a distributional view, ensuring they are not just classified correctly, but also similar to the real minority samples. Actually, we use optimal transport distance here, but other measures like MMD or energy distance could also be employed. We also have an in-distribution version as shown in algorithm 1, which minimizes a combined objective function. This function considers both the classification loss and the distributional differences. The algorithm involves generating synthetic samples, updating them, and then applying a sample rejection step. Beyond the in-distribution version, we also have an auto-distribution algorithm which follows a similar principle. The key takeaway is that we are not just blindly generating data, we are carefully crafting it to be both classifiable and representative. An important part of our method is the sample rejection criteria. We reject synthetic samples that don't adhere to the underlying institution. Synthetic samples should be closer to real samples of the same class than the average distance between real samples within that class. This step further refines the quality of our synthetic data. Now let's look at the results. We evaluated our method on several benchmark datasets. As shown in these tables, our approach consistently outperforms various baselines across different imbalance factors. demonstrating the effectiveness of our distribution matching strategy in improving long-tailed classification performance. Furthermore, our method is also highly versatile. We have shown that it can be effectively combined with other techniques such as revetting methods in long-tailed research. These results shown in Table 3 indicate that our approach consistently reduces test error rates when integrated with other sorter methods. This highlights its adaptability and potential for broader use. Okay, to give you a visual sense, here's the representation visualization. You can see, we can observe that our synthetic samples exhibit better filter alignment with the real samples compared with some baseline methods like M2M. Okay, in summary, our key contribution is a novel framework for synthesizing minority samples that considers both classification confidence and distribution matching. This leads to significant experimental improvement in long-tailed classification and the generation of high-quality synthetic samples. More importantly, our method is also applicable in both in-distribution and auto-distribution settings, making it a valuable tool for a wide range of real-world applications. Thank you.
Okay, thank you. I think given the time, let's take our coffee break before the coffee get cold. So, okay, let's take let's come back in 3:30. When we will have our second invited talk.
Recording in progress.
No, it's not mine. Thank you. Hello, Professor Wang, are you there? Are you there online?
Yeah, I'm here. Hi.
Okay, great. I think at your convenience, I think we can start your talk. And probably
Okay.
you want to share your screen.
Okay. Wait a moment. Okay, can you see the screen?
Oh, yeah, we are seeing it.
Okay.
Probably you want to put it in a full screen also.
Does it work?
Yes, we are seeing it. I think it's fine. It's all right. Yeah.
Okay, thank you.
Okay, so probably let's start our second half of the workshop. And we will begin with our second invited talk, presented by Professor Xiangfeng Wang from the School of Computer Science and Technology and the School of Mathematical Science, East China Normal University. And Professor Wang gonna talk about structured and efficient optimization algorithms for large-scale optimal transport. And please join me on welcoming Professor Wang. And originally, Professor Wang planned to join us in person, but due to some unforeseen changes of circumstances, he couldn't come, so he's joining online. So let's welcome Professor Wang for his great talk.
Okay, thank you. And thank you for the invitation. And it's my honor to be here to to discuss and present some of our some of the works in our group.
Sorry to interrupt, Professor Wang. Is there any chance if you can turn on your video or anything so the audience
Can
could
you
see
see?
you?
Okay, no problem.
We are seeing the slides. We are seeing the slides okay, but if possible, right? So, but if
Yes,
it's not convenient,
I think it's convenient.
okay, then probably
Can you see the
let's
video? Can you
continue.
see the camera?
I don't think we can see it in yeah, oh here, yeah, yes, perfect. Yes, I think we can see you in a very small window, but that's fine. Thank you so much. Please continue. Sorry.
Okay, thank you. And good afternoon, everyone. Thanks for coming. And my name is Xiangfeng Wang. I'm from East China Normal University. Today I'm very excited to talk about the structured and efficient optimization algorithms for large-scale optimal transport. And we will explore how we can effectively compare large data sets, and particularly when the data isn't all in one place, using some inexact proximal point technique and the decentralized entropic optimal transport techniques. And here is what we will cover today. We will begin with the basics of optimal transport, what it is and where it came from. And we'll discuss why this is important today, the motivations and the challenges, especially with large-scale data. We will look at an efficient algorithm, the fast proximal point algorithm for approximating optimal transport. And the main focus will be on decentralized entropic optimal transport. I will briefly show some experimental results and discuss some summary and future work. Let's start with a core concept, optimal transport. I think all of you are very familiar with. This idea dates back over 2 centuries to Monge. He posed a seemingly simple question: if you have a pile of sand or soil and want to move it to form differently shaped pie somewhere else, what is the most efficient way to do it? What transport plan minimize the total effort or cost? Fundamentally, optimal transport provides a powerful geometric framework for comparing probability distributions. It doesn't just look at point-wise differences. It considers the cost of moving probability mass from one distribution to match the other. In discrete setting, which we will focus on initially, we often represent distributions as a histogram of probability vectors. Imagine a vector A in Rn space, where all elements AI is non-negative and sum to 1. Each AI represents the mass of the distribution located at a specific point xi. We can write the discrete measure formally using a Dirac delta function where delta xi represents a unit mass concentrated entirely at location xi. A related classic problem is the optimal assignment problem, and workers and tasks and cost matrix Cij for work I doing task j. The goal is to find a one-to-one assignment, maybe a permutation of the task, and that minimize the total cost. The original problem for discrete measures seeks a deterministic map T that pushes the mass from alpha to exactly match beta. This means for every target location Yj, the total mass mapped to it must equal Bj. And also the objective is to find the map T minimizing the total transport cost, where Cxy is the cost of moving mass from X to Y. And in the special case where we have endpoints in each distribution and always are equal, the Monge problem essentially becomes the assignment problem where the map T corresponds to a permutation sigma, which means Txi equals Y sigma I. However, the Monge formulation is intuitive, but it has limitations. It often requires the distributions to have the same number of points. And finding the optimal map T can be computationally hard. It's a non-convex combinatorial problem, and Kontorovich proposed a relaxation that overcomes these issues instead of a strict one-to-one or many-to-one map T. He allowed mass from a single source point xi to be split and sent to multiple targets yj. This is represented by a coupling matrix or transport plan P, where Pij is the amount of mass moved from xi to yj. This plan P must satisfy the marginal constant. The total mass leaving xi must equal ai, and the total mass arriving at yj must equal bj. Mathematically, the set of all valid transport plans P satisfying these constraints is denoted as the set UAB, and this set is a convex polyton, which is very important. And the Kontorovich optimal transport problem is then find the plan P that minimize the total transport cost, calculated as the expected cost Cp. This minimum values is the Kontorovich optimal transport cost. Why is this relaxation so powerful? It first transforms the problem into a linear programming problem, which is convex and much easier to solve computationally than the original problem. It's more or in comparison between distributions with different numbers of points or different total masses, though typically normalized. And crucial for problems like the assignment problem, where among solution exists, a Kontorovich relaxation is tight. Its optimal solution corresponds to the amount solution. However, while the Kontorovich formulation is a convex linear programming problem, solving large-scale linear programming problems can still be computationally demanding. A major advancement came with the introduction of entropic regularization. Instead of minimizing just the cost, we minimize a slightly modified objective. And here the HP is the entropy of the transport plan P, defined as HP. And also the parameter epsilon is the regularization strength. Entropy favors smoother or more spread out transport plans. Adding this strictly convex entropy term has significant benefits. And also the regularized problem becomes strictly convex or epsilon strongly convex, and we can guarantee a unique optimal solution P epsilon. And this unique solution P epsilon has a remarkable structure. It can be expressed in the form P epsilon, while the matrix, the core matrix K is the Gibbs kernel matrix, and UV are positive scaling vectors. These scaling vectors are chosen to ensure the marginal constraints. This structure leads directly to a very simple and efficient iterative algorithm called Syncol. And the Syncol algorithm alternates between updating U and V to satisfy the marginal constraints. And this algorithm, the Syncol algorithm, can converge very quickly in practice because the core operations are matrix to vector multiplications. It can be highly parallelizable and scales well, making it the workhorse for approximating optimal transport distances in many applications. And it's also worth noting that the Syncol algorithm can be interpreted as a block coordinate ascent method on the dual formulation of the entropic optimal transport problem, while the dual variable f and g are related to the scaling vectors by UV. Then we recall the entropic regularization optimal, and the entropic regularization gives a fast approximation to the original Kontorovich optimal transport cost. The accuracy depends on the parameter epsilon, and a smaller epsilon is more accurate, but can be numerically unstable, while larger epsilon is stable, but gives a very loose approximation. What if we want to want the original and unregularized solution, but still want efficiency? And here we introduce the proximal point algorithm, and the proximal point algorithm offers a way. It's an iterative scheme to solve the original problem. At each step, we can find the next iterate PL+1 by solving a subproblem that balances minimizing the original cost and staying close to the previous iterate PL. And here the distance dh is a Bregman divergence measuring the distance between PL, and gamma controls the proximity emphasis. If we choose the Bregman divergence based on the entropy, the update step becomes equivalent to solve an entropically regularized optimal problem, but with a modified matrix, which is blue here. Now, solving this regularized subproblem exactly at each step might still involves many Syncol iterations. We can employ the Syncol algorithm to solve this subproblem. And the key idea is the inexact proximal point method for optimal transport. We can only implement only one single iteration. And to solve this subproblem inexactly by performing just one single iteration. And this gives a computationally cheap update step that still can converge to the solution of the original and regularize the optimal transport problem. And this is, we also call this the fast proximal point algorithm for optimal transport. And we can see the process very clearly here. And for the original entropic regularization case, and the single can find a solution which is a little bit not too close to the optimal solutions. And also if we solve each subproblem we introduced in the fast proximal algorithm, and we can by step by step procedure to get closer to the exact optimal solution. And then if we only introduce one single iteration here, we will use more iterations, but we can still get close to the optimal solution. And take the Wasserstein-GAN as an example. This efficient optimal algorithm, especially the fast proximal point algorithm, have unlocked many applications, especially for the Wasserstein-GANs. Instead of problematic divergence like the GS or KL, the WGAN can employs the optimal transport, especially the Wasserstein distance, as the loss function to train a generate network. And this often leads to a more stable training. Computing the gradient involves the optimal transport plan and its dual potentials. The RP2T algorithm and the faster proximal point algorithm can be used here to efficiently approximate the OT distance and its gradient. And we combine the original SDD algorithm, and given current estimation, we can obtain the optimal transport plan P star, and then use the envelope theorem estimated derivatives of the Wasserstein distance. And some numerical experiments on mini data set for image generation. We can find that if we employ the RPOT, especially the fast proximal point algorithm, we can generate more practical and more cases of the mini data set than the other case that we use a single algorithm to solve each optimal transport problem and to estimate the gradient. And beyond this, the optimal transport is fundamental for comparing distributions in various crucial machine learning tasks. For example, here, the first one is domain adaptation. And in this case, aligning feature distributions from a source domain where the labels are available and the target domain where labels are not available. And also the generative modeling like the WGAN problem we just discussed, and using the optimal transport map itself as a generative model, or evaluating the quality of generated samples. And also the multimodal alignment, finding correspondence between data from different modalities, like aligning images and text descriptions in large vision to language models. However, a major challenge arises in the area of big data and large models like the GPT, Llama, DeepSeek, or Qwen. Data is often too massive to fit on a single machine and is inherently distributed across multiple servers, devices, or organizations. Trying to compute the optimal transport in these scenarios by first gathering all data to a central server is often infeasible due to, for example, the communication bottlenecks. And it's not easy to transferring huge data set, and transferring huge data set is slow and costly. And also the storage limitation is still an issue. A central server might not able to hold the combined data set, and the privacy concerns. Raw data often cannot be shared due to the privacy regularizations or confidentiality agreements. Therefore, we need methods that can compute the optimal transport problem or compare distributions directly in a decentralized manner, and minimizing the communication and the privacy and preserving the data privacy. And this also brings us to the core topic in this talk, the decentralized entropic optimal transport. And we consider the entropic optimal transport problem. We consider a problem like this. And the key to decentralization lies in its dual form. This can be written as maximizing an expectation where the f epsilon function involves both u and v, and the kernel term, the kappa xy, now considering the distributed setting, and the source data mu is split into L to the source domain data mu is split into mu1 to mu L, mu I, for example, across I agents, and the target data gamma is split into gamma 1 to gamma j across j agents, and the overall expectation involves pairs of agents I and j. In reality, communication might be constrained by a network topology or protocol represented by probabilities that agent I can communicate with agent J. The accurate objective optimized might use E instead of the ideal P times Q, leading to the W epsilon. There is a potential protocol mismatch error, which is bounded if the communication protocol E isn't too close from the ideal case. And discretizing with N samples for agent I and Ni samples for agent I and Mg samples for agent J. Objective involves optimizing local dual variables Ui and Vj associated with agents. The computation requires evaluating terms involving the kernel block Kij. And the kernel block matrix Kij is a very important that we need to consider. And the crucial challenge is how can agent I and agent J compute or approximate their contribution involving Kij without directly sharing their raw data samples. One powerful approach proposed in ICLR 2021 applies when the kernel kappa xy can be viewed as a generalized inner product. For instance, GIP, meaning it's a function of the inner product xy and the norm. The idea is to use random projections, form of locality sensitive hashing, or agents share a set of p random vectors. Each source agent I computes a binary script of its data by checking the sign of the projections. Similarly, target agents compute A gamma J. Remarkably, the inner product XY can be approximated using only these binary scratches and the norms. Let's call this approximation maybe kappa hat, and the error is bounded and decreases with the number of projections P. This allows approximating the necessary kernel blocks without exchanging raw data, and only the compressed scratches and norms privacy of norms need consideration. And based on this kernel approximation, we can introduce the decentralized entropic optimal transport algorithm, and it has 3 key steps. The first one is to compute and broadcast the scratches. Each source agent I compute its scratch A mu I, and each target agent J computes A gamma J. These scratches are exchanged between communicating agents. And then we go to the step 2. We update the dual variables through another optimization algorithm called the mini-batch randomized block quantity descent algorithm. Agents now iteratively update their local dual variable mu I and vj. We use a mini-batch randomized block quantity descent approach. In each iteration, a subset of agents might be activated, and an activate agent I receives scratches from its communication partners and computes the approximated local objective term and updates its own variables mu I. This optimization uses only the scratches, preserving privacy of the raw data. And then we go to the step 3. We compute and broadcast the EOT. After a sufficient number of iterations, the dual variables converge. Each pair of communication agents can compute their contributions to the total objective using the final dual variables and the approximated kernel. These local objective values are aggregated across the network to compute the final estimate of the decentralized EOT distance. And here is the diagram. In the first step, we need to compute and broadcast the scratches, and each source agent computes its own scratch, and each target agent computes its own scratch. These scratches are exchanged between communication agents, and then update dual variables through the mini-batch randomized block quantity descent, and then compute and broadcast the distance. And this is step 2. Following the privacy-preserving objective, we employ the mini-batch randomized block quantity descent algorithm. In each iteration, a subset of the agents might be activated. An activate agent I receives scratches from its communication partners and compute the approximated local objective term and update its UI or VJ if it's the target agent. The optimization uses only these scratches, preserving the privacy of the raw data. And then this is the step 3. We compute and broadcast the entropic optimal transport distance. After a sufficient number of iterations, the dual variables will be converged, and each pair of communication agents compute their own contribution to the total objective using the final dual variables and the approximated kernel. These local objective values are aggregated across the network to compute the final estimation of the decentralized entropic distance. And also we can give some theoretical analysis of the total error. We can analyze the total approximation error. This error has several components. The first one is the convergence error from the convergence error, and which calculates how close the mini-batch randomized block quantity descent optimization methods gets to the optimal of the approximated objective. And this error will decrease with the iteration t. And the second one is the kernel error. The error due to using the approximated kernel instead of the true kernel. And it also decreases with the more projections p. And the third one is the statistical gap. An error from using finite samples instead of the true distributions, and also it will decrease with more samples n and m. And then the protocol mismatch error due to the communication constraint E, differing from the ideal case, and it also depends on on sigma. And the overall error bound combines these factors, showing how the approximation quality depends on number of iterations, samples, projections, and also the communication network. and some experiments on different kinds of applications. And like the first one is the domain adaptation, and also we do some experiments to show whether the introduced decentralized entropic optimal transport algorithm can work for domain adaptation. We can find that both combined with some existing optimal transport algorithm and also the centralized keys. And for the centralized keys, we involved the EMD and sinkhole, also some other SOTA method, OTLPL1, and then compared with our methods, our decentralized keys method, the MRBCDK, and also we introduced the approximated kernel matrix K hat. And for this case, we can find that if we employ the decentralized mini batch randomized block quantities in the method, we can guarantee them the best score, and we can solve the domain adaptation problem more efficiently, and also we can preserve the privacy. Also, more experiments on other cases on other more other domains, and we also compared with the centralized keys. We can find that the MRBCDK and the MIBCDK hat, we can guarantee the almost the best score, and also the MRBCD with the true matrix K will get the better score than the keys that with approximated kernel matrix K hat. Overall, let's discuss. Let me give some summary, and also we discuss some works that we want to do in the future. In this talk, the main case is that I want to show is to give two important optimization algorithms to calculate the structured optimal transport problem. The first one is to introduce the inexact proximal point algorithm, and the inexact technique like the linearization or proximal point techniques can be employed to calculate the exact optimal transport problem instead of the entropic regularized case. And the second one is the decentralized algorithm. And also if we consider the dual formulation of the optimal transport problem, and we can introduce some decentralized techniques, and also we can both calculate the problem in decentralized case and also preserve the privacy, and also we can employ the approximated kernel matrix techniques to show the efficiency. And also in the future, we will transfer the especially the decentralized keys from discrete probability measures to continuous ones, which we have not discussed in the talk. And also the theoretical bound is not very tight. Let us double check. And especially for the convergence error is related to the optimization algorithm we employed, like the BCD algorithm, the block quantity descent algorithm, which we can design more efficient optimization algorithm to tighter this bound. For the kernel error, for the kernel error, which is related to the approximation of the kernel, maybe we can employ more efficient kernel approximation algorithm to tight this bound. However, for the mismatch, for the protocol mismatch error, which is related to the communication constraints, we cannot do more work on this because it's related to the communication constraint. And also more applications maybe will introduce more challenges like the application that we discussed here. For the large scale vision language alignment problem, which is very popular now for the multimodal large foundation models, and also the decentralized algorithm that we introduced here can help to train the vision to language or multimodal large foundation model efficiently and without and with preserving the privacy of the raw data. The first algorithm, the fast proximal algorithm, is published on UAI maybe a few years ago. And if you are interested, you can read our paper. And for the second one, the decentralized entropic optimal transport for privacy preserving distributed distribution comparison, which is a comparison work with Professor Hong Tong. And also, if you are interested in this work, you can find it on arXiv. Okay. And thank you for your attention and thanks for the listening. And this is my talk. Thank you.
Okay, let's thank Professor Wang for his informative and in-depth talk. So we have some time for questions if there is any questions from the audience. So let me check whether we have online questions. Then probably I have a question to Professor Wang. So I think I have a similar question to our last invited speaker. So like today, everyone is talking about large language models. We can see like a large proportion of papers in top conferences in both machine learning and data mining, such as Trimble W here. So and as a researcher on optimal transport, I probably want to hear about your thoughts on optimal transport's role in the area of large language models.
Excuse me, I can't hear the question exactly. Can you repeat?
Yeah. So I was just asking, what do you think about optimal transport on large language models?
Okay. I think we can apply or we can introduce the optimal transport to large language models or just the multimodal large foundation models. Both. The first one that we can redesign some loss functions maybe in the large language model, and also we can design some alignment loss functions for the multimodal large foundation model. And this is the one case. And for the other direction, we can also use the large language models for us to design the optimal transport algorithm. For instance, because the for instance, the optimization algorithms we designed to solve the optimal transport problem more efficiently, they are all presented in codes. And also we can introduce the large language model to redesign or to modify the codes that we produce. We produced, for example, the exact proximal point algorithm. We can employ the large language model to modify the codes or modify the algorithm for some self-tuning of the parameters or some other cases to directly modify the codes that we produced to solve the optimal transport problem.
Okay, thank you. Thank you for the great answer. I think let's thank Professor Wang again, and we can move to our next talk.
Okay, thank you.
Okay, so thank you. Thank you so much. So I think Professor Wang's talk ended earlier than planned, so we have So previously so let me move our first spotlight talk here. So let's just go to the so probably I would like to invite the authors of the first spotlight talk. Yes, and coming on the stage. So is there? There should be also the first one. Oh yeah. Oh, the second one. Sorry, my apologies. So the second one, please. The second, the author of the second spotlight talk, please come on stage. And which one is your? Yeah. Which one is yours?
Yeah, this one, second one.
Second one. And is there one there? Do you want to use this? I don't.
Oh, yeah.
Yes.
Hello, everyone. I'm very honored to be invited to give a talk about our paper, Calibrating Tabular Anomaly Detection via Optimal Transport. My name is Han Ye, one of the authors of this paper from Jilin University. First, we study the problem of tabular anomaly detection, which aims to identify the minority of outliers from the majority of inliers, as illustrated in this figure. Since labeling anomalies is time-consuming and often requires a lot of efforts for annotations, thus tabular anomaly detection is often implemented in semi-supervised learning, where only normal sample Cs are available during the training time. And in the test time, we have both anomalous and normal sample Cs. And typically, TAD problem often aims to train a predictive model, FX, that is able to generate an anomaly score for each sample of interest, where higher anomaly score means higher confidence that a sample belongs to the anomaly category. However, there are some fundamental challenges for TAD problem. First is data heterogeneity. Tabular data features are heterogeneous that contains both categorical features and numerical features. In addition, there are no annotations for anomaly types in the training time. Thus, it is a challenge for our to accurately identify the anomaly types. Therefore, the existing methods often rely on some implicit assumptions about the anomaly types, where the assumptions will often be violated across a diverse real-world tabular data sets. Therefore, instead of looking for a universal winner assumption that is unlikely to exist, our method proposed to empower the models with adaptability to different tabular data. And we leverage the benefits of prior knowledge in any well-trained TAD models, and then calibrate the output of the TAD models by performing adaptive and sample-specific error correction, which is formulated by calculating by calibration the original anomaly score S by one.
You share the screen. One moment. Sorry.
Okay. Let's come back. So we propose to calibrate Okay. So we propose to calibrate at the end the well-trained TAD model's output by perform adaptive and sample-specific error correction, which is formulated by calibrating the original anomaly score S by one error correction delta, where the expected delta for anomalous category is higher than the expected delta for normal category. This is our proposed method. We first propose to model the normal train set with two methods. One is random sampling, a subset with size M, denoted as distribution P, and the other is applying k-means clustering method, denoted as distribution Q. And the distribution P is represented by the distribution across M random samples. And the other distribution Q is represented by the distribution across K centers generated by the k-means clustering method. And since distribution P and Q are used to model the same normal train set, thus it is reasonable to assume that distribution P and Q should be similar. Given P represented by M random samples and Q represented by K centers, and the P and Q are similar, we can consider one thing. What will happen if we extend P by adding one sample X star of interest? We assume that if the X star is from normal category, they will result in minimal change to the discrepancy between distribution P and Q. In contrast, if X star is from anomalous category, it will increase the discrepancy between distribution P and Q if we extend P by X star from anomalous category, then extend P by X star from normal category. We propose to model the discrepancy between distribution P and Q by optimal transport. And in our paper, we have theoretically proved that if we use optimal transport to model the distance between distribution P and Q, their distance will be higher if we extend P by X star from anomalous category than extend P by X star from normal category. Therefore, the sample-specific error correction item can be calculated by computing the optimal transport distance between distribution P and Q, denoted as delta star, and we can use the delta star as the error correction item to calibrate the original anomaly score S star. This is our overall algorithm, given any well-trained TAD model. And our CTAD method is model agnostic, and it requires no training time. It requires only inference time. First, we will obtain distribution Q across K centers, and then for each X star from test set, we will obtain a distribution P and then extend P by X star, then calculate delta star by calculating the optimal transport distance between distribution P and Q. And then we will use the delta star to calibrate the original anomaly score S star. And in our experiment, we have conduct comparison by CTAD method over 9 well-trained TAD models and over 30 tabular data sets. And the overall performance shows that our city method achieves the SOTA performance. In summary, instead of looking for a universal winner assumption that is unlikely to exist across a diverse tabular datasets, we proposed a model-agnostic method to calibrate existing TLD methods via optimal transport. That's all. Thanks for listening.
And any questions for the speaker?
Hello. Thank you for the talk. How will you choose the K value in the experiment?
Sorry?
How will you choose the K value in the experiment? The K, the number of cluster in K mean.
Okay. Typically we set the centers around 10, and we find that if we increase the number of clustering, it will not increase the performance significantly.
Yeah. How the K value affect to the accuracy of anomaly detection?
Sorry.
How the K value affect to the accuracy?
Affect to accuracy?
Yeah.
In our experiment, we find that if we increase the number of clusters and the AUC ROC score is increased gradually and then stable in the test time.
Stable, but is it good or not? I mean, when K is tend to a big value, so is it a good accuracy or?
Sorry.
I mean, when the K is tend to a big value.
So a weak value?
A big value. I mean, let's say
small value.
Let's say the K is equal to M. So how about the accuracy?
Okay. I see. We don't conduct this such experiments. I will explore it.
Yeah. Okay, thank you.
Okay, thanks.
Okay, thank you. Let's invite our next speaker on the stage. So I'm inviting the spotlight of invariant representation learning from discrete perspective.
Do I have to say the screen again?
No, you can use which one is your slide? Oh, this one should be this one, right? This one, right? Is that your slide? It's, yeah, if you want to use this, just in case.
Hi everyone. My name is Tung Long Vương. I'm from Monash University, and I'm excited to be here to present our work, invariant representation learning from discrete perspective. Yeah, sorry about that. We consider the problem of learning invariant representation from in the domain generation setting. So let me introduce the setting first. In
sharing problem? Yeah. It's still the previous slides, yeah. Okay. It should work now. It should work. Okay. Thank you.
So let me introduce the setting of domain generation first. the goal of domain generation is to train a model on the data from certain training domain and enable it to perform well on the unseen domain. For example, here we have the images from in different style, such as sketch, cartoon, and art painting. And we expect that the model will perform well on realistic photo which it had never seen before. Another practical scenario of domain generation is the problem of autonomous car. For example, the autonomous car is developed and trained on the US road, but when the car is sold to Europe, we also expect that the car also operates reliably on the Europe street. Sorry for and in environment representation learning is dominant approach to address the domain generation problem. And however the for example, in the previous example, we can see that the shape of animal remain consistently across both training and testing domain. So the underlying intuition here is that there will be a underlying factor that should be invariant across domain. However, in recently we only can learn the invariant representation from the training domain and ensure that it invariant with respect to the training domain. However, in our prior work, we also saw that such representation still benefit to domain generation setting. But the problem we want to solve here is that the invariant representation usually learned by representation alignment method. But we in our analysis we will show that this method for to capture the truly training invariant feature. And to address that problem, we propose a novel method called subspace representation alignment to capture the invariant feature in training domain under universal and with only male assumption. And here is our assumption on the data generation process. It is depicted in the figure 1 here. For in our setting, we assume that the label information only depend on the causal factor, but the observation can be vary due to the invariant factor. For example, for the case of autonomous car, maybe the shape of vehicle on the road is invariant factor, but the background or the weather condition can be considered as the environment variable. And now we turn to the question how to learn the invariant representation under our setting. First, we can directly infer the first condition from the assumption of data generation. We call that the label information is only depend on the causal factor. So it implies that the invariant representation and the environment specific representation should be conditional independent given the neighbor information, and this condition can be addressed by using the alignment method. Particularly, we minimize the divergence between the latent distribution across domain, and we also saw the second condition that the optimal hypothesis should be the optimal predictor over across training domain. And two conditions can be optimized by following objective function. You can see here that in the first term is the domain offset, and the second term is the representation alignment term, which minimize the divergence between the latent distribution across domain. And this divergence can be the hard divergence, or Harringer distance, or even Waterstain distance. But however, in recently some theoretical papers show that there's a trade-off between the two terms here. If there discrepancy in the neighbor marginal distribution across domain, we cannot simultaneously minimize both terms. So this implies that the existing method based on the representation alignment approach fail to truly capture the invariant representation. So however, we observe that based on our data generation process, we observe that if the sample with the same class conditional probability, they are come from the same or equivalent causal factor. So if we can group this sample into single subspace, and we can simultaneously optimize the knot and the alignment in with the trade-off in the within the subspace. So and here is our result. We saw that if we use the optimal hypothesis capture from the training domain, we use it as a subspace indicator. For example, we can assign the we can group the sample based on the prediction of the optimal hypothesis here. We can remove the neighbor frequency in between domain. So we can optimize both terms at the same time. And in next slide, we will present how to implement this idea based on the discrete perspective. Here in the first step, we will train the model on training domain and learn the optimal hypothesis. After that, we can assign the subspace index to example based on the prediction of the optimal hypothesis here. Just ignore this one now, but sorry for that. And in the second step, we can group the sample based on the subspace index in the first step, and do alignment by minimize the divergence between the latent distribution within each subspace. For example, here we can use a hard divergence based on the deploy the decorator, for example, in GAN. And however, we observe that when we use directly use the prediction from the optimal hyperacid to assign the subspace, we observe that the cardinality of the subspace index set is too large and makes the optimization is challenging. So to address this problem, we propose to model the subspace index set by set of liquid representation. And the idea is that we can think that about kind of clustering. First, we endow an set of finite subspace liquid. Finite set of liquid representation, and we endow an decreased distribution over that set. After that, we can minimize the water stain distance between the latent distribution and the liquid distribution over the subspace set. So this objective you can refer to water stain mean with pressure định vùng present in earlier. So when combine all of these objectives, we got the final objective here with the not about the hyperacid and subspace prediction and subspace alignment. And here is our experiment. We evaluate our method on well-known domain derivation benchmark dataset, and the results show that our method consistently outperform the base repeated baseline on all dataset. And the second one is the application study about the number of subspace. It means the number of liquid representation in the index set. And we can see that when we increase the number of subspace, the performance will increase. But when the number of subspace become too large, I think due to the optimization problem, the result is a bit convert and start decrease. Yeah, so that's
yeah. Thank you. Is there any questions for the speaker? Thank you so much. Okay, let's welcome the next spotlight talk speaker, improving generalization in neurotopic models while optimal transport. So, okay. Let me reshare. Let me reshare just in case. Should be working? Should be working? Yep. Okay, if you want to use this, you can reuse. That's good.
Thanks for coming. Here. So first, let me thank to my co-authors, He Zhao and Ding Feng and Lan Du, who give me great support during my research. And here we introduce another application of optimal transport. Particularly is for topic model, and we want to improve the generalization in topic model. Some basic background of topic model. So given a collection of document, the topic model can learn some global topics about the corpus. For example, the yellow one, maybe it's about genes. For the blue one, maybe it's about data. So through these topics, we know the global semantics of the corpus. And another component is the document representations. We call it a topical representation. For each document, the topic model will encode the document as a distribution over the topics. For example, this document have a high weight on the yellow topic. So from the topical representation, we know this document is more about the yellow topic, maybe it's a gene. And I take this figure from David Bliss' work. So that's where we introduce our problem. It's a generalization of the topical representation. So here, given the source document, the topic model can learn some, let's say it's a good representation because they are separate. And through these features, so this representation, we can use it for downstream application. For example, we can use these features as input features to train a classifier for document classification, classifying, or retrieval. But the problem is that when we move to different unseen corpus, in practice, people usually train another topic model. But we're wondering, what if we use this model to infer the representation without retraining? How about the quality of the representation? So that's our target. And our method is very simple. It's based on assumption. If it can generalize the topical representation, the topic model should produce a similar representation with a document after data augmentation. Actually, the idea is quite similar to contrastive learning. We want to move the document with similar semantics close to together in the latent space. So what we need is two things. One is a distance measure to measure the distance of the topical representation between the original document and its augmentation. Another is a augmentation function. Since our workshop is about optimal transport, so we focus on the distance measure. Yeah, we have many choice for distance measure, but here we focus on OT. Why? Because in topic model we have some beautiful characteristic. For example, the distribution, a topical representation is a distribution over topics. The topics have semantics. For example, actually the music and the speed or price, these are topics. They have semantics. And the semantics can be used to construct as a cost matrix to compute the OT. And interestingly, the topics is a distribution over words. Words also have semantics. And here we use cosine distance to compute the distance between words. This can be used as a cost matrix for topical level OT. So we have it's a two-level optimal transport. At the document level, it's a distribution over topics. At the topic level, it's a distribution over words. So because of the characteristic in topic model, we can do this translation. But this calculation is motivated by a previous work called hierarchical optimal transport. But they use it as distance measure. But here we implement to improve neural topic models. Yeah, it's a plug and play module, and we can plug this loss. We call it a generalization and regularization, Greek. We can plug this loss to most VE-based neural topic models. Yeah, it's a graphical view of our method. Here's the main point, the cost matrix. It's an optimal transport between topics. and it's here's our results. And the setting is like this. We train the model on the one source data set, for example, 20 news. And we use this model to infer the topic distribution on unseen documents, and we test its performance. We use three metrics. We use the topic repetitions and features to train downstream classifiers, and we evaluate the performance using these three metrics. And in most cases, we can improve the performance over its base model. And here's a ablation study. We try other distance instead of a topical OT. And we show better generalization ability. And here's another study. We change the experimental setting. Here we change the number of topics. And we can also notice that we have a stable performance when changing the hyperparameter. That's a quick talk of our work. Thanks for listening, and welcome to any questions.
Any question for the speaker? Thank you.
Thank you.
So, okay, so what's left is we have probably three online short talks, and each of them is 5 minutes. So I'm trying to look at whether our speakers are here. So, and because we run over time in the first session, so let me invite the speaker of the last short talk in the first half of the session. The talk name is OT Aligned Representation Surgery for Multi-Time Model Merging. I believe the speaker is here. Can I ask the organizers to yes, I think, yeah. Can the speaker say something so that we can hear you? I think you probably want to invite the speaker as the panelist or something. Yeah, I think so. If for the speaker, can you please share your screen and say something so that we can hear you? You are muted. I think the speaker is muted. We can see your slides, but still cannot hear you. Are you still muted? Yes, you are still muted. The last one, sorry.
Our paper is the OTR and the representation
Hello, can you hear me? I think we are experiencing some lags in the vaccine, 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 vaccine,
Mr. Zhao, can you hear me? I want to change my change her 那个 position. I want to have I want to 那个 show my show the presentation first. Can you hear me?
Yes, we can. We can hear you. Just
We can hear you. 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 I can hear you, but there is a lot noise in there. Okay.
You can try to start now. Can you hear us?
Okay. Good afternoon, everyone. My name is Jihan Liu, a graduate student from Jing University. Today, it's my great honor to represent our collaborative work titled OTTAD, Optimum Transport-Based Deep Learning for Lightweight Tabular Detection, guided by Rui Yingwu from CDN University and Dandan Guo from Jing University. This study is situated in the field of tabular anomaly detection. Traditional methods often struggle to effectively model normal samples, while deep learning-based approach can be computationally intensive. Optimum transport, a technical used to measure distance between distributions, has found widely spread use in data argument and optimization. For enterprise tabular anomaly detection task, the training set contains only normal samples, while the test set includes both normal and anomaly samples. This setup facilitates the construction of normal data distribution for matching purpose. In this paper, we propose a lightweight deep learning approach based on optimum transport for tabular anomaly detection. Specifically, we framed the anomaly detection task as an optimum transport problem within the representation space, and design an efficiently network using multi-layer perceptron. During training, the model learns clusters from normal samples. During testing, anomaly scores are generated by computing the optimum transport distance between the distribution of test samples and the anomaly cluster centers. Our method is as follows. The pipeline can be structured in two stages. The first stage is normal feature extraction and modeling. In training phase, to enhance discriminative information in the data, we employ a lightweight MLP network to extract data representations and use center loss to reduce the distance between representations of normal samples. To better normal the normal distribution, we apply k-means to generate k-cluster centers as the prototypes of normal samples. Then we can formulate the normal distribution as QC. The second stage is batch testing samples detection via optimum transport. In test phase, we firstly obtain the representation of the test batch samples, and then formulate the test distribution as PZ. Then we can learn the transport plan by minimizing the regularized optimum transport distance between these two distributions, which formulate as T star. Finally, the transport metric T star represents the probability of assigning different samples to various cluster centers. Therefore, after judging the cluster metric C, we can calculate the anomaly score S for the S test sample as SI. The experiments are as follows. The performance of our approach is compared to traditional methods, and the method use deeper networks such as GOAD and Natural, and even achieved superior results in terms of both AOC-PR and AOC-RC metrics. Furthermore, compared to DeepSVD, our method improved AOC-PR by 2.3% and AOC-RC by 1.97%. Compared to computational costs on current dataset, our method shows greater efficiency on groups, parameters, and training time. Thank you for your attention. I would be glad to address any question regarding our method.
Thank you. Yeah, thank you. So maybe let's move to the next online presentation, which is next one is it should be the optimal transport-based deep learning for lightweight tabular anomaly detection. Okay, so can you hear me?
Sorry, Mr. Zhao. I was just representing my my PowerPoint. Now turn is Zhang Bingjie.
Sorry. Sorry, what? I didn't. So are you saying that another speaker is with you, or? If we don't have another speaker, maybe. Hello, can you hear me? Are you? I think it seems that another speaker is not online. So I think we can probably call it a day for this workshop. And once again, as the organizers, we thank the workshop chairs, the invited speakers, the general chairs of the conference. We also thank the authors, reviewers, and attendees, and everyone here. And let's call it a day for the workshop. And we hope you will enjoy the main conference of the web conference. Thank you so much.